I want to think a little bit more carefully about how we think about angular momentum for a body that is both rotating and translating. And to get at that, I want to use a sort of simple example. It's the same kind of example that we were using in thinking about how to come up with moment of inertia. So it's an example where we have some kind of barbell, right? It's located at the center mass of that barbell is located at some position R center mass. The barbell is at some angle theta, and I'm interested in knowing what the angular momentum of this barbell is, right? Now I'll remind you, angular momentum is defined as the sum over all the particles in the system of their position vectors crossed with their momentum vectors, okay? And I want to remind you of that because this actually says, when you look at it a little more carefully, angular momentum depends on what you choose as an origin, right? It depends on where you're measuring R from. So if I'm measuring R from here, these positions that I'm interested in are actually the vector that go from the origin to the first mass, and they go from the origin to the second mass, right? And similarly, the momentum that I'm interested in is the momentum as measured by an observer in this reference frame. Okay, so with that in mind, let's come back and now think about how are we going to write down these R's and how are we going to write down these P's. Well, so the position of the first mass I will write down as being this vector that goes from the origin to this. So I'll call that R1. And I'm going to break that down into being the position of the center of mass plus R1 with respect to the center of mass. So I could sort of blow up my dumbbell a little bit and say that this vector is R1, comma C, the vector that goes from the origin to the first mass, the vector that goes from the center mass to the second mass is R2, comma C. Okay. The momentum of the first mass is going to be the velocity, the mass, times the velocity of the center mass, plus the velocity about the center mass. Well, the velocity of this first mass about the center mass, if it's rotating, right, is simply going to be omega times r in the theta 1 hat direction, right? So I could say this is theta 1 hat. Similarly, this guy is going to be, if it's rotating, this will be theta 2 hat. So the momentum of the first mass will be, or the velocity of the first mass will be the velocity of the center mass plus the velocity with respect to the center mass. Velocity with respect to the center mass is going to be omega times whatever this distance r is times theta 1 hat. All right. By the same token, R2 is going to be r center mass plus R2, comma C, and the momentum of the second mass will be m times the velocity of the center mass plus omega times r times theta 2 hat. Okay. All right, so now I know what my positions are. I know what my momenta are. I need to actually do the cross product. And let's think about that cross product. Let's just think about it for the first term. So I'm going to have the first term of R crossed with the first term of P. I'll have the second term of R crossed with the second term of P. I'll have the first term of R crossed with the second term of R crossed with the first term of P, and the first term of R crossed with the second term of P, right? So if I go through and do that out, I'll get the momentum of the first object will be RCOM cross MVCOM, right? I'll get another term that's second times the second. Well, R1 is simply big R times R1 hat. So this will be big R times R1 hat crossed with omega times R times theta 1 hat, right? That's what this term will be. So this is 1, this is 2. If I take R1 cross MV1, I'm going to get, so this is, if this is number 3, I'm going to get big R times R1 hat crossed with MVCOM, right? And then finally, this last term is going to be RCOM cross omega times R times theta 1 hat. Okay, so this is the fourth term. I can do the same thing for this second set, so not surprisingly, the first one will look exactly the same. The second one will be r times r2 hat crossed with omega times r times theta 2 hat. The third will be r times r2 hat crossed with mvcom. And the fourth will be the position vector of the center mass crossed with omega times r times theta 2 hat. Okay. All right, so sorry for the algebra, but let's take a look at what it actually says. So first term here. Each of these terms simply looks like the position of the center of mass crossed with this mass located at the center of mass. In other words, if I were to add all of these together, right, for any object, I would end up getting the position vector of the center of mass crossed with the total mass of the system times the velocity of the center of mass. Okay? In other words, this first term would simply be the position vector of the center of mass crossed with the linear momentum of the system. Okay? The second term, if I look at it, should look pretty familiar from that derivation of moment of inertia, right? I've got r1 hat cross theta 1 hat, which is k hat, r2 hat cross theta 2 hat, which is k hat. I've lost an m here, sorry. So this is m times r squared times omega, right, in the k hat direction. In other words, it's plus the moment of inertia, but it's the moment of inertia actually about the center of mass, so about that axis that goes through the center of mass, times the angular velocity. Okay, so this is what this entire term, right, is L due to rotation about the center of mass. What about these two terms, though? Well, here we've got r1 hat cross VCOM, right? So r1 hat crossed into the velocity of the center of mass. But r2 hat is actually pointing in the opposite direction of r1 hat. So these two terms actually are the negatives of each other. They're going to cancel, right? And similarly, these two terms turn out to be the negatives of each other too, right? We've got RCOM cross theta 1 hat. Well, theta 1 hat points in that direction. RCOM cross theta 2 hat points in the opposite direction. So this cross product is going to be the negative of this cross product as well. So these two terms go away as well. In other words, what we end up getting for the angular momentum of the system is simply the position vector of the center of mass crossed with the linear momentum of the system, right, plus the moment of inertia of the system as measured from the axis that goes through the center of mass times the angular velocity of the system about the center of mass. So in fact, when you break it down this way, what you have is a term that looks like angular momentum due to translation, and then in addition to that, you have angular momentum due to rotation. And in general, when you talk about problems where you have both translation and rotation, this idea that you can break down things into the translational component and the rotational component is a pretty powerful idea. We just walked through something to sort of show you how it actually works out, that that's possible, but that's an idea that you'll want to use multiple times when you start to try to figure out equations of motion for these types of systems.